Hi, welcome to my course, Mastering Data Science, Machine Learning, and Artificial Intelligence from Beginner to Expert. I hope you like it. Chapter 1, Introduction to Data Science. What is data science and why is it important? Data science is an interdisciplinary field that involves the extraction, analysis, and interpretation of large and complex data sets to identify meaningful insights, make informed decisions, and support evidence-based decision-making. It combines techniques and methods from various fields, including statistics, mathematics, computer science, and domain-specific knowledge, to work with structured and unstructured data. Data science is important for several reasons. Number one, improved decision making. Data science enables organizations to make informed decisions based on data-driven insights rather than relying on intuition or subject opinions. Number two, standing of customers. By analyzing large amounts of customer data, organizations can gain standing of their customers' behavior, preferences, and opinions, allowing them to tailor their products and services to meet their customers' needs. The process of data science and its different stages. The process of data science can be broken down in several stages. Number one, problem definition. The first step in process of data science is to define the problem that you are trying to solve. This involves understanding the business problem or scientific question that you are trying to address and determining the relevant data that will be needed to solve it. Number two, data collection. The next step is to collect the data that you will use to solve the problem. This can involve collecting data from various sources, such as databases, web scraping, or through APIs. Number three, data preparation. Once the data has been collected, the next step is to prepare the data for analysis. This involves cleaning the data, dealing with missing values, and transforming the data into a format that can be used by statistical models. Number four, exploratory data analysis, EDA. In this stage, the data is analyzed to identify patterns and relationships in the data. This is typically done through visualizations and statistical analysis. Number five, model development. Once the data has been analyzed, the next step is to develop a model to solve the problem. This involves choosing an appropriate model, such as regression model or machine learning algorithm, and training the model on the data. Number six, model evaluation. After the model has been trained, the next step is to evaluate its performance. This involves testing the model on a separate data set and measuring its accuracy, precision, and recall. Number seven is deployment. The final step is to deploy the model into a production environment where it can be used to make predictions or decisions. Number eight, monitoring and maintenance. The deployment of the model is not the end of the process. It is important to continuously monitor the model to ensure that it is performing as expected and to make any necessary updates to improve its performance over time. These stages form the general framework for a data science project, but the specifics of each project will vary depending on the nature of the problem being addressed and the type of data being analyzed. The process of data science requires collaboration between individuals with diverse skills, including data engineers, statisticians, domain experts, and data visualizers. Different fields that use data science and examples of real-world applications. Data science is used in a wide range of fields and industries to solve a variety of problems. Some of the fields that use data science and examples of real-world applications include: 1. Healthcare. In healthcare, data science is used to analyze patient data to predict disease outbreaks, improve patient outcomes, and personalize treatment plans. For example, data science can be used to predict which patients are most likely to be readmitted to the hospital based on their medical history and other factors. Number 2, finance. In finance, data science is used to identify fraud, detect financial anomalies, and make informed investment decisions. For example, data science can be used to identify unusual patterns in financial transactions that may indicate fraudulent activity. Number 3, retail. In retail, data science is used to analyze customer data to improve the customer experience, optimize pricing strategies, and increase sales. For example, data science can be used to personalize product recommendations for customers based on their browsing and purchase history. Number 4, manufacturing. In manufacturing, data science is used to optimize production processes, improve quality control, and reduce waste. For example, data science can be used to predict which manufacturing processes are most likely to produce defects based on sensor data and other factors. Number 5, transportation. In transportation, data science is used to optimize logistics, reduce fuel consumption, and improve safety. For example, data science can be used to predict which routes are most efficient for delivery trucks based on traffic patterns and other factors. Number 6, sports. In sports, data science is used to analyze player performance, predict game outcomes, and make informed decisions about player scouting and drafting. For example, data science can be used to analyze the performance of basketball players to determine which players are most likely to be successful at the next level. Number 7, energy. In energy, data science is used to optimize energy production and consumption, reduce waste, and improve sustainability. For example, data science can be used to predict which wind turbines are most likely to need maintenance based on sensor data and other factors. These are just a few examples of the many fields that use data science to solve real-world problems. The applications of data science are vast and continue to expand as the field grows and evolves. Overview of the tools and techniques used in data science. There are many tools and techniques used in data science, and the specific tools and techniques used will depend on the nature of the problem being solved and the type of data being analyzed. Some of the most commonly used tools and techniques in data science include: number 1, programming languages. Data scientists often use programming languages like Python and R for data analysis and modeling. These languages have a large number of libraries and tools for data manipulation, visualization, and machine learning. Number 2, SQL. Structured Query Language is a database management language that is used for managing and retrieving data from relational databases. Number 3, data visualization. Data visualization is an important tool for data exploration and communication of results. Tools like Matplotlib, Seaborn, and Plotly are commonly used for creating visualizations in data science. Number 4, machine learning algorithms. Machine learning algorithms are used to build models that can automatically make predictions or decisions based on data. Common machine learning algorithms include linear regression, decision trees, random forests, and neural networks. Number 5, natural language processing, NLP. NLP is a field of computer science and artificial intelligence concerned with the interactions between computers and human language. NLP techniques are used in data science for tasks like sentiment analysis, top, topic modeling, and text classification. Number 6, deep learning. Deep learning is a subset of machine learning that is based on artificial neural networks with multiple hidden layers. Deep learning is used in data science for tasks like image classification, speech recognition, and natural language processing. Number 7, big data technologies. Big data technologies like Hadoop, Spark, and NoSQL databases are used to process and store large amounts of data. These technologies are critical for working with big data, which is often too large to be processed by traditional database management systems. Number 8, and one of my favorite, cloud computing. Cloud computing platforms like AWS, Google Cloud, and Microsoft Azure provide data scientists with the computing power and storage they need to work with large amounts of data. These are just a few examples of the many tools and techniques used in data science. The field is constantly evolving, and new tools and techniques are being developed all the time. Data scientists must stay up to date with the latest tools and techniques in order to effectively solve the problems they are facing. Chapter 2, Data Collection and Pre-Processing. Sources of data and methods of collecting data. Data is the lifeblood of data science, and there are many sources of data that data scientists can use to solve problems. Some of the most common sources of data include: number 1, surveys and questionnaires. Surveys and questionnaires are one of the most common methods of collecting data. They can be used to gather information on a wide range of topics, including demographics, opinions, and behaviors. Number 2, public data sets. There are many public data sets available on websites like Kaggle, UCI Machine Learning Repository, and data.gov. These data sets can be used for a wide range of purposes, including research and education. Number 3, social media. Social media platforms like Twitter, Facebook, and Instagram provide a wealth of data that can be used to analyze sentiment, opinions, and behaviors. Number 4, log files. Log files from websites, apps, and other systems can provide valuable data about user behavior and performance. Number 5, sensors. Sensors can be used to collect data from the physical world, including data on temperature, humidity, air quality, and more. Number 7, scraping data. Scraping data is the process of extracting data from websites and other sources. Data scraping can be used to gather data from sources that are not easily accessible through APIs or other methods. Number 8, APIs. Many websites and applications provide APIs that allow data to be collected and analyzed. APIs can be used to collect data on a wide range of topics, including weather, stock prices, and social media activity. The method of collecting data will depend on the specific problem being solved and the type of data being collected. Data scientists must carefully consider the sources of data they use, and they must be aware of any limitations or biases that may be present in the data. It is also important to consider the ethical and legal implications of collecting and using data. Understanding and cleaning data. Understanding and cleaning data is a critical step in the data science process. Data often comes from multiple sources and is often in a messy and inconsistent format, so it must be cleaned and transformed before it can be used for analysis and modeling. Some of the tasks involved in understanding and cleaning data include: number one, data exploration. This involves exploring the data to understand its structure, relationships, and patterns. Data exploration is often done using visualizations and basic statistics. Number two, handling missing data. Missing data is a common problem in real-world data sets. Data scientists must decide how to handle missing data, which may involve imputing missing values or removing observations with missing values. Number three, handling outliers. Outliers are extreme values that can have a significant impact on the results of analysis and modeling. Data scientists must identify and handle outliers, which may involve removing them or transforming the data to reduce their impact. Number four, feature engineering. Feature engineering involves creating new features or transforming existing features to improve the performance of machine learning models. Normalization, data normalization. Data normalization is the process of transforming data so that it has a mean of 0 and a standard deviation of 1. This is often done to reduce the impact of scale on machine learning algorithms. Number six, encoding categorical variables. Categorical variables are variables that take on a limited number of values, such as male or female. Data scientists must encode categorical variables as numerical values so that they can be used in analysis and modeling. These are just a few examples of the tasks involved in understanding and cleaning data. The specific task will depend on the nature of the data and the problem being solved. Data scientists must be meticulous and thorough in their data cleaning process, as the quality of the data will directly impact the quality of the results. Dealing with missing and duplicate values. Handling missing and duplicate values is an important step in the data cleaning process. Missing values are a common issue in real-world data sets and can negatively impact the results of analysis and modeling. There are several ways to handle missing values, including: number one, inputting missing values. This involves replacing missing values with the estimates based on the existing data. This can be done using simple methods like mean imputation or more advanced methods like multiple imputation. Number two, removing observations with missing values. This involves removing observations with missing values from the data set. This is a simple solution, but it can result in a loss of information. Number three, removing features with missing values. This involves removing features with a high proportion of missing values from the data set. This can be done to reduce the impact of missing values on the analysis and modeling. Duplicate values. Duplicate values. Values are another common issue in real-world data sets. Duplicates can occur due to data entry errors, system errors, or other reasons. Duplicates can negatively impact the results of analysis and modeling, so they must be removed. There are several methods for removing duplicates, including number one, removing duplicates based on single feature. This involves removing duplicates based on the values of a single feature, such as an ID or name. Number two, removing duplicate based on multiple features. This involves removing duplicates based on the values of multiple features, such as ID and date. It's important to choose the right method for handling missing and duplicate values, as the choice can have a significant impact on the results of analysis and modeling. Data scientists must also be careful not to introduce new errors or biases when handling missing and duplicate values. Feature engineering and selection. Feature engineering and selection are important steps in the data science process. They involve creating new features and selecting the most relevant features for analysis and modeling. Feature engineering involves creating new features or transforming existing features to improve the performance of machine learning models. Some common methods for feature engineering include number one, binning. Binning involves dividing continuous variables into discrete bins, which can reduce the impact of noise and outliers. Number two, encoding categorical variables. Categorical variables are variables that take on a limited number of values, such as male or female. Data scientists must encode categorical variables and numerical values so that they can be used in analysis and modeling. Number three, interactions. Interactions involve combining two or more features to create a new feature. This can capture complex relationships between features that may not be apparent from individual features. Feature selection. Feature selection involves selecting the most relevant features for analysis and modeling. This is important because using too many features can lead to overfitting and decrease model performance, while using too few features can result in underfitting. Some common methods for feature selection include number one, correlation-based feature selection. This involves selecting features that have a strong correlation with the target variable. Number two, recursive feature elimination. This involves removing features one by one and evaluating the performance of the model after each removal. The process is repeated until the best set of features is found. Number three, regularization. Regularization is a method for preventing overfitting by adding a penalty term to the cost function that discourages the model from using too many features. Number four, wrapper methods. Wrapper methods involve evaluating the performance of the model for different subsets of features. The best subset of features is then selected based on performance. Feature engineering and selection are iterative processes that require experimentation and refinement. The specific methods used will depend on the nature and of the data and the problem being solved. Data scientists must be careful not to overfit the data and must carefully evaluate the performance of the models to ensure that the best features are being used. Chapter 3, Exploratory Data Analysis. Univariate and multivariate analysis. Univariate and multivariate analysis are techniques used in data science to understand the distribution and relationship between variables. Univariate analysis involves examining each variable individually. This can provide insight into the distribution of the variable, including measures of central tendency, mean, median, and mode, and dispersion, range, variance, standard deviation. Univariate analysis is useful for understanding the distribution of a single variable, but it does not capture relationships between variables. Multivariate analysis involves examining the relationship between two or more variables. Some common methods for multivariate analysis include: number one, correlation analysis. Correlation analysis involves calculating the correlation between two or more variables. Correlation ranges from -1 to 1, with -1 indicating a strong negative correlation, 1 indicating a strong positive correlation, and 0 indicating no correlation. Number two, regression analysis. Regression analysis involves fitting a line or a curve to the data to capture the relationship between two or more variables. Regression can be used for both linear and nonlinear relationships. Number three, principal component analysis. PCA is a dimensionality reduction technique that involves transforming the data into a lower dimensional space while preserving as much of the original variance as possible. This can be useful for visualizing the relationship between variables in high-dimensional data. Number four, cluster analysis. Cluster analysis involves grouping similar observations into clusters based on their similarity. This can be useful for exploring the structure of the data and discovering patterns in the relationships between variables. Univariate and multivariate analysis are important steps in the data science process, as they provide insight into the relationship between variables and help data scientists to select the most relevant variables for analysis and modeling. The specific methods used will depend on the nature of the data and the problem being solved, but it is important to choose the appropriate methods and to carefully evaluate the results. Data visualization techniques. Data visualization is an important aspect of data science that involves creating visual representations of data to aid in understanding and communication. Some common data visualization techniques include: number one, bar charts. Bar charts are used to compare values across categories. They can be used to compare quantities or proportions. Number two, line charts. Line charts are used to visualize trends over time. They are commonly used to show changes in a single variable over time. Number three, scatter plots. Scatter plots are used to visualize the relationship between two variables. They can be used to identify patterns, outliers, and trends in the data. Number four, histogram. Histograms are used to show the distribution of a single variable. They can be used to show the frequency of occurrences for different ranges of values. Number five, box plots. Box plots are used to show the distribution of a single variable. They show the median, quartiles, and outliers of the data. Heat maps. Heat maps are used to show the relationship between two variables. They can be used to identify areas of high and low values as well as trends in the data. Number seven, pie charts. Pie charts are used to show proportions. They are commonly used to show the distribution of a single variable across categories. Number 8, dot plots. Dot plots are used to show the distribution of a single variable. They are similar to bar charts, but each value is represented as a dot rather than a bar. Data visualization is an important tool for data scientists as it can help to quickly and effectively communicate insights from data. When creating visualization, it is important to choose the appropriate technique for the data and the story being told, and to use appropriate labeling, scaling, and coloring to clearly communicate the message. Identifying relationships and patterns in data. Identifying relationships and patterns in data is an important aspect of data science. Some common techniques for identifying relationships and patterns in data include 1. Correlation analysis. Correlation analysis involves calculating the correlation between two or more variables. Correlation ranges from -1 to 1, with -1 indicating a strong negative correlation, 1 indicating a strong positive correlation, and 0 indicating no correlation. Correlation analysis can be used to identify relationships between variables and to assess the strength and direction of those relationships. Number 2, regression analysis. Regression analysis involves fitting a line or a curve to the data to capture the relationship between two or more variables. Regression can be used for both linear and nonlinear relationships. Regression analysis can be used to make predictions about one variable based on the values of another variable. Number 3, principal component analysis, PCA, is a dimensionality reduction technique that involves transforming the data into a lower dimensional space while preserving as much of the original variance as possible. This can be useful for visualizing the relationship between variables in high-dimensional data. Number 4, cluster analysis. Cluster analysis involves grouping similar observations into clusters based on their similarity. This can be useful for exploring the structure of the data and discovering patterns in the relationship between variables. Number 5, association rule mining. Association rule mining is a technique used to identify relationships between variables and transactional data. It is commonly used in market basket analysis to identify which items are frequently purchased together. Number 6, time series analysis. Time series analysis involves analyzing data over time to identify trends and patterns. Time series analysis can be used to make predictions about future values based on historical data. These are just a few of the many techniques used to identify relationships and patterns in data. The specific techniques used will depend on the nature of the data and the problem being solved, but it is important to choose the appropriate methods and to carefully evaluate the results. Data visualization can also be a powerful tool for identifying relationships and patterns in data, as it can help to quickly and effectively communicate insights. Chapter 4, Statistical Modeling. Overview of statistics and probability. Statistics and probability are essential components of data science. Statistics is the branch of mathematics that deals with the collection, analysis, interpretation, presentation, and organization of data. Probability is the branch of mathematics that deals with the study of random events and their outcomes. Here's a brief overview of the topics covered in statistics and probability. Number 1, descriptive statistics. Descriptive statistics involves summarizing and describing the characteristic of a data set. Common descriptive statistics include measures of central tendency, mean, median, and mode, and measures of variability, range, variance, and standard deviation. Number two, inferential statistics. Inferential statistics involves making predictions and inferences about a population based on a sample of data. Inferential statistics techniques include estimation and hypothesis testing. Number three, probability. Probability is the study of random events and their outcomes. It deals with the likelihood of events occurring and the calculation of the probabilities of different outcomes. Number four, probability distributions. Probability distributions are mathematical models that describe the probabilities of different outcomes in a random event. Common probability distributions include the normal distribution, the binomial distribution, and the Poisson distribution. Number five, sampling and sampling distributions. Sampling and sampling distributions are key concepts in the inferential statistics. Sampling refers to the process of selecting a subset of the data to represent the population. Sampling distribution describe the distribution of statistics calculated from samples. Confidence intervals. Number six. Confidence intervals are a range of values that are calculated from a sample of data and are used to estimate the range of values that are likely to contain the true population parameter. Number seven, hypothesis testing. Hypothesis testing is a statistical procedure that involves testing a claim or hypothesis about a population parameter based on sample of data. These are just a few of the many topics covered in statistics and probability. Understanding these concepts and techniques is essential for data scientists as they are used to make inferences and predictions from data, to evaluate the reliability of results, and to make data-driven decisions. Introduction to regression and classification models. Regression and classification models are two of the most commonly used types of machine learning models in data science. Number one, regression models. Regression models are used to predict a continuous numerical output based on one or more input variables. Regression models attempt to find the best fitting line or curve that describes the relationship between the inputs and the output. Common regression models include linear regression, polynomial regression, and decision trees. Number two, classification models. Classification models are used to predict a categorical output based on one or more input variables. Classification models attempt to find the best fitting boundary that separates the different categories based on the inputs. Common classification models include logistic regression, k-nearest neighbors, and support vector machines. Overfitting and underfitting. Overfitting and underfitting are two common challenges in machine learning. They refer to situations where a model is too complex or too simple, respectively, to effectively capture the underlying relationship in the data. Number one, overfitting. Overfitting occurs when a model is too complex and fits the noise in the data rather than the underlying pattern. This leads to a model that performs well on the training data but poorly on new, unseen data. Overfitting is a common problem in machine learning, especially in models with many parameters such as decision trees and neural networks. To prevent overfitting, data scientists can use techniques such as cross-validation, regularization, and early stopping. Cross-validation involves splitting the data into several subsets, training the model on one subset, and evaluating its performance on the other. Regularization is a technique that adds a penalty term to the model to reduce its complexity and prevent overfitting. Early stopping involves monitoring the performance of the model during training and stopping the training process when the performance on a validation set stops improving. Number two, underfitting. Underfitting occurs when a model is too simple to capture the underlying relationship in the data. This leads to a model that performs poorly on both the training and test data. Underfitting is a common problem in machine learning when the model is not complex enough to capture the underlying patterns in the data. To prevent underfitting, data scientists can try using more complex models such as deeper neural networks or decision trees with more nodes. They can also try adding more features to the data or transforming the existing features to capture more information. In summary, overfitting and underfitting are two common challenges in machine learning and data science. Understanding these concepts and how to prevent them is essential for building effective models that generalize well to new, unseen data. Model evaluation and selection. Model evaluation and selection are critical steps in the machine learning process. They involve determining how well a model is performing on the data and selecting the best model for a given problem. 1. Model evaluation metrics. To evaluate the performance of a model, several metrics can be used, including accuracy, precision, recall, F1 score, mean squared error, root mean squared error, and R squared. The choice of evaluation metric will depend on the problem being solved and the type of model being used. For example, accuracy is a commonly used metric for classification problems, while MSE or RMSE are commonly used for regression problems. Number two, cross-validation is a technique used to evaluate the performance of a model on new, unseen data. The data is divided into several folds, and the model is trained on one fold and evaluated on another. This is repeated several times, with each fold serving as the test set once. The performance of the model is then averaged over the different folds to obtain a more robust estimate of its performance. Number three, model selection. After evaluating the performance of several models, the data scientist must select the best model for the problem. This can be done by comparing the evaluation metrics for each model and selecting the one with the highest performance. Other factors such as computational complexity, interpretability, and ability to generalize to new data should also be considered when selecting the best model. In summary, model evaluation and selection are essential steps in the machine learning process. Understanding and using the appropriate evaluation metrics and techniques can help data scientists build effective models that generalize well to new, unseen data. Chapter 5, Machine Learning. Introduction to Machine Learning. Machine learning is a subset of artificial intelligence that focuses on the development of algorithms that can learn patterns in data and make predictions based on those patterns. In machine learning, the goal is to build models that can automatically improve their performance as they are exposed to more data. There are several different types of machine learning, including number one, supervised learning. Supervised learning involves training a model on labeled data, where the outcome variable, also known as the response or dependent variable, is known. The model is then used to make predictions on new, unseen data. Examples of supervised learning include regression and classification problems. Number two, unsupervised learning. Unsupervised learning involves training a model on unlabeled data where the outcome variable is not known. The goal is to find patterns or relationships in the data without a specific target variable. Examples of unsupervised learning include clustering and dimensionality reduction. Number three, reinforcement learning. Reinforcement learning involves training a model through a series of trials and rewards. The model is trained to take specific actions in response to its environment in order to maximize a reward signal. Reinforcement learning is commonly used in robotics and control systems. Machine learning algorithms are trained on large amounts of data and are designed to automatically improve their performance over time. They can be used for a wide range of applications, including image and speech recognition, natural language processing, and predictive modeling. In summary, machine learning is a rapidly growing field that combines computer science and statistics to develop algorithms that can learn from data and make predictions. Understanding the basics of machine learning is essential for anyone interested in data science and artificial intelligence. Different types of machine learning algorithms. There are several different types of machine learning algorithms, each designed to solve specific problems or address specific needs. Some of the most common types of machine learning algorithms include linear regression. Number one is a supervised learning algorithm used for predicting a continuous outcome variable based on one or more predictor variables. It assumes a linear relationship between the predictors and the outcome. Number two, logistic regression. Logistic regression is a supervised learning algorithm used for predicting a binary outcome variable. It is used in classification problems where the goal is to predict a categorical outcome based on one or more predictor variables. Number three, decision trees. Decision trees are a type of supervised learning algorithm used for both regression and classification problems. They use a tree-like structure to represent the relationship between the predictors and the outcome. Number four, random forests. Random forests are an ensemble learning technique that combines multiple decision trees to improve the accuracy of predictions. They are commonly used for both regression and classification problems. Number five, K nearest neighbors. KNN is a non-parametric instance-based learning algorithm used for classification and regression problems. It works by finding the K nearest neighbors to a given sample and using the mean or mode of the neighbors' classes as a prediction for the sample. Number six, support vector machines. SVM is a supervised learning algorithm used for classification and regression problems. It works by finding the boundary that best separates the classes or predicts the outcome. Number seven, naive Bayes. Naive Bayes is a probabilistic algorithm used for classification problems. It works by assuming independence between the predictor variables and calculating the probabilities of each class based on the predictor values. Number eight, neural networks. Neural networks are a type of machine learning algorithm inspired by the structure and function of the human brain. They are used for a wide range of applications, including image and speech recognition, natural language processing, and predictive modeling. These are just a few of the many types of machine learning algorithms available. The choice of algorithm will depend on the type of problem being solved and the characteristics of the data. In general, it is a good idea to try several different algorithms and compare their performance to determine the best fit for a given problem. Overfitting and regularization. Overfitting occurs in machine learning when a model is too complex and fits the training data too closely, resulting in poor generalization to new, unseen data. This can lead to high training accuracy but low test accuracy, as the model has learned the noise in the training data instead of the underlying patterns. Regularization is a technique used to address overfitting in machine learning models. It involves adding a penalty term to the loss function that the model is optimizing, which penalizes certain model parameters if they are too large. This helps to reduce the complexity of the model and prevent overfitting. There are several types of regularization techniques, including L1, lasso, regularization, L2, ridge regularization, and elastic net regularization. The choice of regularization technique will depend on the type of problem being solved and the characteristic of the data. In general, regularization can help to improve the generalization performance of a machine learning model and reduce the risk of overfitting. It is an important tool in the data scientist toolkit and should be used in conjunction with other techniques such as cross-validation and early stopping to obtain the best possible results. Feature scaling and normalization are techniques used to pre-process data in machine learning. They are important because many machine learning algorithms use the magnitude of the features to weight the importance of each feature. And if the features are not at the same scale, some features may dominate others. Feature scaling involves transforming the features so that they are on the same scale. This can be done by dividing each feature by its maximum value, or by subtracting the mean and dividing by the standard deviation. The goal is to make sure that all features are on the same scale so that they are treated equally in the machine learning algorithm. Normalization, on the other hand, involves transforming the features so that they have a Gaussian distribution with zero mean and unit variance. This is useful because many machine learning algorithms assume that the data is normally distributed, and normalizing the data can help to make the algorithms work better. Both feature scaling and normalization are important pre-processing steps that can help to improve the performance of machine learning algorithms. It is a good idea to perform these steps before training the model to ensure that the data is the correct format for algorithms to use. Chapter 6, Supervised Learning. Linear regression and logistic regression. Linear regression and logistic regression are two commonly used regression algorithms in data science and machine learning. Linear regression is a supervised learning algorithm used for predicting continuous variables, such as the price of a house or the weight of a person. It is based on the assumption that there is a linear relationship between the dependent variable and the independent variables. In linear regression, the goal is to fit a line or a hyperplane in higher dimensions to the data that minimizes the sum of squared residuals. Logistic regression, on the other hand, is a supervised learning algorithm used for binary classification, where the goal is to predict a binary outcome. Logistic regression is a type of generalized linear model, and it uses a logistic function to model the relationship between the independent variables and the dependent variable. The logistic function maps any input to a value between 0 and 1, which can be interpreted as the probability of the positive class. Both linear regression and logistic regression are widely used in data science and machine learning, and they are simple and easy to understand. They are also widely used as a starting point for more complex algorithms such as decision trees and neural networks. Understanding how linear and logistic regression work is an important step towards becoming a data scientist and or machine learning practitioner. Decision trees and random forests. Decision trees and random forests are two commonly used machine learning algorithms for classification and regression problems. A decision tree is a tree-like model that is used to make decisions or predictions by recursively splitting the data into subsets based on the values of the features. Each node in the tree represents a feature, and the branches represent the possible values of that feature. The leaves of the tree represent the final prediction. The goal is to split the data in such a way that the target variable becomes more and more predictable at each node. Random forests, on the other hand, are an extension of decision trees that use an ensemble of decision trees to make a prediction. In a random forest, many decision trees are grown using a random subset of the features and a random subset of the data. The predictions of the individual trees are then combined to make the final prediction. This combination can be done by taking the average of the majority vote. Random forests are more accurate and robust than decision trees, and they reduce overfitting and improve the stability of the predictions. They are widely used in many real-world applications such as credit risk assessment, customer segmentation, and stock market prediction. In summary, decision trees and random forests are powerful and versatile algorithms that are widely used in data science and machine learning. Understanding how they work and when to use them is an important step towards becoming a successful data scientist or machine learning practitioner. Support vector machines. Support vector machines are a type of supervised machine learning algorithm used for classification and regression problems. The main ideal behind SVM is to find a hyperplane, a line, or a plane in high dimensional space that separates the data points into different classes or predicts the continuous target variable. SVMs work by transforming the data into a higher dimensional space and finding the hyperplane that has the maximum margin, which is the distance between the hyperplane and the closest data points, also known as support vectors. The maximum margin hyperplane is preferred because it provides the best generalization performance, meaning it is less likely to overfit the data. SVMs have several advantages over other machine learning algorithms, such as good performance on high dimensional data, ability to handle nonlinear decision boundaries, and the ability to handle large amounts of data efficiently. SVMs are widely used in many real-world applications, such as text classification, image classification, and bioinformatics. Understanding how SVMs work and when to use them is an important step towards becoming a successful data scientist or machine learning practitioner. Neural networks and deep learning. Neural networks and deep learning are a subset of machine learning algorithms inspired by the structure and function of the human brain. They are used for a wide range of tasks, including image classification, speech recognition, natural language processing, and recommendation systems. A neural network consists of multiple layers of interconnected nodes called artificial neurons. Each neuron receives input from other neurons and produces an output that is passed to the next layer of neurons. The neurons are connected by weights, which determine the strength of the connection between neurons. The goal of training a neural network is to find the optimal weights that minimize the error between the predicted output and the true output. Deep learning refers to the use of deep neural networks which have multiple hidden layers. The hidden layers allow the network to learn complex representations of the data, making it possible to perform tasks that are beyond the capability of shallow neural networks. Deep learning has revolutionized the field of machine learning and computer vision, achieving state of the art results on many tasks. It has been applied to various real world problems such as self driving cars, sentiment analysis, and facial recognition. In summary, neural networks and deep learning are powerful and complex algorithms that have a wide range of applications in data science and machine learning. Understanding how they work and when to use them is an important step towards becoming a successful data scientist or machine learning practitioner. Chapter 7, Unsupervised Learning. Clustering algorithms. Clustering is a type of unsupervised learning where the goal is to group similar data points into clusters. Clustering algorithms do not rely on pre-existing labels or categories, making them useful for exploring and discovering patterns in data. There are several popular clustering algorithms, including number one, k-means. K-means is a centroid-based algorithm that works by defining k-centroids in the feature space and assigning each data point to the nearest centroid. The centroids are then updated in each iteration to reflect the mean of the data points in the corresponding cluster. Number two, hierarchical clustering. Hierarchical clustering algorithms work by merging or splitting existing clusters until the desired number of clusters is reached. There are two main types of hierarchical clustering: agglomerative, which starts with individual data points and merges them into clusters, and divisive, which starts with all the data points in a single cluster and divides them into smaller clusters. DB-scan. DB-scan, which stands for Density-Based Spatial Clustering of Applications with Noise, is a density-based algorithm that works by identifying areas of high density in the feature space and grouping data points that are close together into clusters. Number three, Gaussian mixture model. GMM is a probabilistic model that assumes that each cluster is generated by a Gaussian distribution. The algorithm estimates the parameters of the Gaussian distribution and assigns each data point to the cluster with the highest likelihood. Clustering algorithms have a wide range of applications in data science, including customer segmentation, image segmentation, and anomaly detection. Understanding how different clustering algorithms work and when to use them is an important step towards becoming a successful data scientist or machine learning practitioner. Dimensionality reduction. Dimensionality reduction is a technique used to reduce the number of features in a dataset while retaining as much information as possible. The goal of dimensionality reduction is to simplify the data so that it can be more easily analyzed and visualized. There are two main types of dimensionality reduction: feature selection and feature extraction. Feature selection involves selecting a subset of the original features to use the analysis, while feature extraction involves transforming the original features into a new, lower dimensional feature space. Examples of feature extraction techniques include: 1. Principal component analysis. PCA is a linear method that transforms the data into a new coordinate system where the first principal component has the highest variance, the second principal component has the second highest variance, and so on. Number 2, linear discriminant analysis. LDA is a linear method that seeks to maximize the separation between different classes in the feature space. Unlike PCA, LDA is a supervised method and requires knowledge of the class labels. Number 3, TSNE. T, distributed stochastic neighbor embedding, is a nonlinear method that maps the data into 2 or 3 dimensional space for visualization. TSNE is particularly useful for visualizing high dimensional data and is often used in the exploratory stage of data analysis. Number 4, autoencoders. Autoencoders are neural network-based models that can be used for dimensionality reduction by encoding the data into a lower dimensional representation and then decoding it back to the original space. Dimensionality reduction is an important technique in data science and machine learning as it can reduce noise and computational costs and make it easier to visualize complex data sets. Understanding how different dimensionality reduction techniques work and when to use them is an important skill for data scientists and machine learning practitioners. Anomaly detection is a technique used to identify instances in a data set that do not conform to the expected pattern or behavior. These instances, also known as anomalies, can be outliers, errors, or even fraudulent activities. Anomaly detection is a crucial step in many applications, such as fraud detection in financial transactions, fault detection in industrial processes, and intrusion detection in cybersecurity. There are two main types of anomaly detection: supervised and unsupervised. In supervised anomaly detection, the model is trained on labeled data to identify anomalies, while in supervised anomaly detection, the model is trained on unlabeled data to identify patterns and anomalies in the data. Examples of unsupervised anomaly detection techniques include: 1. Statistical methods. These methods use statistical measures such as mean and standard deviation to identify anomalies based on the deviation from the mean. Number 2, density-based methods. These methods identify anomalies based on the density of data points in the feature space. Points that are far from other points are considered anomalies. Number 3, clustering methods. These methods group similar data points together and identify anomalies as points that do not belong to any group. Examples of supervised anomaly detection techniques include: number 1, decision trees and random forests. These algorithms can be used to identify anomalies by learning the decision boundaries that separate normal data points from anomalies. Number two, support vector machines. SVMs can be used to identify anomalies by learning a boundary that separates normal data points from anomalies in the feature space. Number three, neural networks. Neural networks can be used to identify anomalies by training the network to reconstruct normal data and then using the reconstruction error to identify anomalies. Anomaly detection is an important step in the data science process as it helps identify errors, outliers, and unusual patterns in the data, which can have a significant impact on the results of data analysis and machine learning models. Chapter 8, Reinforcement Learning. Markov decision processes. Markov decision processes are mathematical models used to model decision-making problems in which the outcome of each decision depends on only the current state of the system rather than its history. They are widely used in fields such as economics, engineering, operations research, and artificial intelligence. An MDP is defined by four components. Number one, a set of states. This represents the different possible states of the system. Number two, a set of actions. This represents the different decisions and can be made in each state. Three, a transaction function. This defines the probability of transitioning from one state to another after taking an action. Number four, a reward function. This defines the reward or cost associated with each action. The objective of an MDP is to find the best policy, which is a mapping from states to actions that maximizes the expected cumulative reward over time. This is done by solving the Bellman optimality equation, which defines the value of a state as the expected cumulative reward starting from the state. There are two main approaches to solving MDP: value iteration and policy iteration. In value iteration, the value of each state is updated until it converges to the optimal value, while in policy iteration, the policy is updated by greedily choosing the action that maximizes the expected reward in each state until it converges to optimal policy. MDPs are widely used in various applications, such as decision making in finance, recommendation systems, robotics, and game theory. In these applications, MDPs provide a framework for decision-making problems in which the outcomes of actions depend on the current state of the system. They help decision makers identify the best actions to take based on the current state of the system, the rewards associated with each action, and the probabilities of transitioning from one state to another. Q-learning. Q-learning is a reinforcement learning algorithm that is used to find an optimal policy for an agent to follow in a Markov decision process. The goal of Q-learning is to learn the optimal action value function, which is a mapping from states and actions to expected rewards. In Q-learning, the algorithm updates its estimate of the action value function based on the observed reward and the estimated value of the next state. The algorithm starts with an initial estimate of the action value function and iteratively updates this estimate based on the observed reward and the estimated value of the next state. The algorithm uses the following update rule. As you can see above, where S is the current state, A is the current action, R is the observed reward, Y is the discount factor, S is the next state, A is the action taken in the next state, is the learning state rate, Q is the estimated action value function for state S, and action A, max Q, say is the maximum estimated action value for the next state S. The Q learning algorithm continues updating the action value function until it converges to the optimal action value function. The optimal action value function is the function that maps states and actions to the expected cumulative reward that results from following that policy. Q learning has been applied to a wide range of problems, including robotics, game playing, and recommendation systems. It has been shown to be effective in solving problems with large state and action spaces where other reinforcement learning algorithms may fail. Policy gradient methods are a class of reinforcement learning algorithms that aim to directly optimize or mapping from states to actions rather than the value functions. The goal of policy gradient methods is to find the policy that maximizes the expected cumulative reward. In policy gradient methods, the policy is represented as a differentiable function, such as a neural network, and is optimized using gradient descent. The policy is updated in the direction of gradient of expected cumulative reward with respect to the policy parameters. The policy gradient can be estimated using Monte Carlo sampling, where the expected cumulative reward is estimated by averaging over a large number of trajectories generated by the current policy. Alternatively, the policy gradient can be estimated using importance sampling, where the expected cumulative reward is estimated using a set of trajectories generated by a reference policy. There are several variants of policy gradient methods, including reinforce, actor-critic methods, and trust region policy optimization. Reinforce is a simple policy gradient algorithm that directly optimizes the policy using gradient ascent. Actor-critic methods combine policy gradient methods with value-based methods such as Q-learning to address the high variance of policy gradient methods. Trust region policy optimization is a more advanced policy gradient method that uses a trust region constraint to stabilize policy optimization. Policy gradient methods have been applied to a wide range of problems, including robotics, game playing, and recommendation systems. They have been shown to be effective in solving problems with complex, high-dimensional state and action spaces, where the optimal policy is not easily represented as a simple function of the state. Chapter 9: Artificial Intelligence. Definition and history of artificial intelligence. Artificial intelligence is a field of computer science that aims to create systems that can perform tasks that typically require human intelligence, such as recognizing speech, understanding natural language, making decisions, and solving problems. AI systems can be designed to perform these tasks using a variety of techniques, including machine learning, deep learning, computer vision, and natural language processing. The history of artificial intelligence can be traced back to the 1950s, when researchers first began exploring the ideal of building machines that could perform tasks that were typically performed by humans. Early AI research focused on developing systems that could perform specific tasks such as playing chess or solving mathematical problems using rules-based system or simple decision trees. In the 1980s and 1990s, AI research shifted towards the use of machine learning algorithms, which are algorithms that can learn from data to make predictions or decisions. This shift was driven by advances in computer hardware and algorithms, which allowed AI systems to process large amounts of data and learn from it. In the late 1990s and early 2000s, deep learning algorithms were introduced, which are algorithms that use artificial neural networks to learn complex representations of data. Deep learning algorithms have been responsible for many breakthroughs in AI, including improved speech recognition, computer vision, and natural language processing. Today, AI is used in a wide range of industries, from healthcare and finance to transportation and retail. It is used for tasks such as diagnosing diseases, predicting stock prices, detecting fraud, and powering virtual assistants. AI is also being used to solve some of the world's biggest challenges, such as reducing energy consumption, improving education, and protecting the environment. Overall, the field of artificial intelligence has come a long way since its early days and is continuing to evolve and grow as advances are made in computer hardware and algorithms. Types of artificial intelligence and their applications. There are several types of artificial intelligence, each with its own unique set of characteristics and applications. Some of the most common types of AI include: number one, rule-based systems. Rule-based systems are AI systems that make decisions based on a set of predefined rules. They are typically used in applications where the decision-making process can be formalized and the rules can be easily specified. Examples of rule-based systems include expert systems used in medicine, finance, and law. Number two, machine learning. Machine learning algorithms are algorithms that can learn from data to make predictions or decisions. There are several types of machine learning algorithms, including supervised learning, unsupervised learning, and reinforcement learning. Machine learning is used in a wide range of applications, including image classification, speech recognition, natural language processing, and recommendation systems. Number three, deep learning. Deep learning is a type of machine learning that uses artificial neural networks to learn complex representations of data. Deep learning algorithms are used in applications such as computer vision, speech recognition, and natural language processing. Number four, natural language processing. Natural language processing is a subfield of AI that focuses on the interaction between computers and humans using natural language. NLP is used in applications such as text classification, sentiment analysis, and machine translation. Number five, computer vision. Computer vision is a subfield of AI that focuses on enabling computers to interpret and understand visual information from the world. Computer vision is used in applications such as image classification, object detection, and facial recognition. Number six, robotics. Robotics is the branch of AI that focuses on the design and development of robots. Robotics is used in applications such as manufacturing, transportation, and healthcare. And lastly, number seven, general AI. General AI, also known as artificial general intelligence, is a type of AI that is capable of performing any intellectual task that a human can. Currently, this type of AI does not exist but is an area of active research. Each type of AI has its own unique set of strengths and weaknesses and is used in different applications depending on the problem it is trying to solve. The field of AI is constantly evolving, and new types of AI are being developed as advances are made in computer hardware and algorithms. Natural language processing and computer vision. Natural language processing and computer vision are two important subfields of artificial intelligence. Natural language processing is a subfield of AI that focuses on the interaction between computers and humans using natural language. NLP involves the use of algorithms to analyze, understand, and generate human language. NLP is used in applications such as text classification, sentiment analysis, machine translation, and chatbots. Computer vision, on the other hand, is a subfield of AI that focuses on enabling computers to interpret and understand visual information from the world. Computer vision uses algorithms to analyze and understand images, videos, and other visual data. It is used in applications such as image classification, object detection, facial recognition, and image processing. Both NLP and computer vision are rapidly growing fields, with new advancements and applications being developed all the time. The combination of NLP and computer vision has led to the development of innovative systems such as visual question answering, where a system can answer questions about images using natural language, and image caption generation, where a system can generate a textual description of an image. Overview of deep learning and its applications. Deep learning is a subfield of machine learning that is based on artificial neural networks with multiple layers. Unlike traditional machine learning algorithms, deep learning algorithms can automatically learn and improve from experience without being explicitly programmed. Deep learning algorithms are inspired by the structure and function of the human brain, with layers of interconnected nodes that process and pass information to each other. These networks can be trained on large amounts of data, allowing them to learn complex patterns and relationships. Deep learning has a wide range of applications, including number one, computer vision. Deep learning algorithms are used in computer vision tasks such as image classification, object detection, and segmentation. They can also be used for video analysis, for example, in video classification or activity recognition. Number two, natural language processing. Deep learning algorithms are used in for NLP tasks such as sentiment analysis, machine translation, and text classification. They can also be used for speech recognition and synthesis. Number three, recommender systems. Deep learning algorithms can be used to develop recommender systems that can make personalized recommendations to users based on their past behavior and performance preferences. Number four, predictive maintenance. Deep learning algorithms can be used to predict equipment failures, allowing maintenance to be performed before it becomes critical. Number five, fraud detection. Deep learning algorithms can be used to detect fraudulent activities in financial transactions by analyzing patterns and behaviors in large amounts of data. Number six, healthcare. Deep learning algorithms can be used to analyze medical images and diagnose diseases, or to predict patient outcomes and recommend treatments. These are just a few examples of the many applications of deep learning. The field is rapidly evolving, and new uses and applications are being discovered all the time. Chapter 10, Ethics and Bias in AI. The impact of AI on society and ethics. Impact of artificial intelligence on society is a highly debated topic with both potential benefits and drawbacks. Some of the potential benefits include: number one, increased efficiency and productivity. AI can automate many tasks, freeing up humans to focus on higher level and more creative work. Number two, improved decision making. AI algorithms can analyze large amounts of data and provide insights and recommendations, helping humans make more informed decisions. Number three, better healthcare. AI can be used in healthcare to diagnose diseases, predict patient outcomes, and recommend treatments, improving patient outcomes and overall healthcare quality. Number four, enhanced safety. AI can be used in safety critical applications such as autonomous vehicles and industrial automation, reducing the risk of human error. However, there are also potential drawbacks to the increasing use of AI in society, including: number one, job displacement. AI can automate many jobs, potentially leading to job loss and unemployment. Number two, bias and discrimination. AI algorithms can perpetuate and amplify existing biases in the data they are trained on, leading to discrimination in decision making processes. Number three, lack of transparency. AI algorithms can be complex and difficult to understand, making it difficult to assess their decision making processes and outcomes. Number four, privacy concerns. AI algorithms can collect and use large amounts of personal data, raising concerns about privacy and the responsible use of this data. The ethical implications of AI are closely related to these potential drawbacks and raise important questions about the responsible development and deployment of AI technology. These questions include: number one, responsibility for outcomes. Who is responsible when an AI system makes a decision that causes harm or discrimination? Number two, privacy. How can personal data be collected, used, and stored in a way that respects privacy rights? Number three, bias. How can an AI system be developed and used in a way that minimizes bias and discrimination? Number four, transparency. How can AI systems be made transparent and accountable so that their decision making processes can be understood and trusted? These are complex and challenging questions and require ongoing discussion and collaboration between AI researchers, developers, policymakers, and society as a whole. Ensuring the responsible and ethical development and use of AI is crucial for maximizing its benefits and minimizing its drawbacks, and is an important consideration for anyone working in the field of AI. Bias in AI and its implications. Bias in AI is a significant concern as it can perpetuate existing societal biases and discrimination in decision making. Bias in AI algorithms can arise from the data that is used to train the model design, or the way the model is used. For example, if the training data contains biased information, then the model will learn that bias and replicate it in its predictions. Similarly, the model design can also contain bias For example, if certain variables are given more weight in the model. The implications of bias in AI can be far reaching and can result in unequal treatment and discrimination of certain groups. For example, biased algorithms in the criminal justice system have led to racial discrimination and have had a disproportionate impact on minority communities. Bias in AI can also impact areas such as employment, lending, and insurance, leading to unequal access to opportunities and resources. To mitigate bias in AI, it is important to be aware of its potential and to take steps to address it throughout the development and deployment of AI systems. This includes collecting and using diverse and representative data, examining algorithms for bias and making adjustments as necessary, and regularly monitoring and auditing AI systems to ensure they are free from bias. Additionally, involving diverse stakeholders in the development and deployment of AI systems can help to identify and address potential sources of bias. In conclusion, understanding and addressing bias in AI is crucial for ensuring fair and ethical decision making and for avoiding negative impacts on society. Fairness and accountability in AI. Fairness and accountability are two important concepts in the use of artificial intelligence systems. Fairness refers to the idea that AI systems should treat all individuals equally and without discrimination. This means that AI systems should produce similar outcomes for individuals who are similarly situated, regardless of their race, gender, religion, or any other characteristic. Accountability refers to the responsibility for the decisions made by the AI systems and the ability to understand and explain how those decisions were made. This is important because AI systems can have significant impacts on individuals and society, and it is essential to be able to hold those responsible accountable for their actions. In practice, ensuring fairness and accountability in AI systems can be challenging, particularly when dealing with complex models that are difficult to understand and interpret. However, there are several strategies that can be employed to help address these challenges. For example, it is important to ensure that the training data used to develop AI systems is diverse and representative and to monitor the performance of AI systems for signs of bias and discrimination. Additionally, AI systems can be designed to be transparent and interpretable so that their decisions can be understood and accounted for. In conclusion, fairness and accountability are critical components of responsibility AI development and deployment. Ensuring that AI systems are fair and accountable will help to promote trust in the technology and to minimize the potential for harm. For avoiding bias in AI models. Avoiding bias in AI models is a complex and ongoing challenge, but there are several best practices that can help minimize the risk of bias. Here are some key steps to consider. Number one, use diverse training data. Ensure that your training data is diverse, representative, and accurately reflects the real-world population you are modeling. This helps to reduce the risk of introducing biases into your models. Number two, monitor performance. Regularly evaluate the performance of your AI models to identify any biases that may emerge over time. This can involve monitoring key performance metrics such as accuracy and fairness and looking for signs of systematic disparity between different groups. Number three, test for bias. Use specific tests and metrics to detect and measure bias in your models, such as demographic parity and equal opportunity. This can help you identify and address areas of concern before they become bigger problems. Number 4, ensure interpretability. Make sure that your models are transparent and interpretable so that you can understand why they are making certain decisions. This makes it easier to identify and address sources of bias and to develop solutions that reduce the risk of harm. Number 5, consider ethical and societal implications. When building and deploying AI models, it's important to consider the ethical and societal implications of your work. This includes considering the potential consequences of your models for different groups and ensuring that your models are aligned with widely accepted ethical and societal values. By following these best practices and continuously monitoring and evaluating the performance of your AI models, you can help to reduce the risk of bias and promote more responsible and ethical AI development. Chapter 11, Conclusion. Recap of key concepts and takeaways. In this course, we covered a wide range of topics related to data science, machine learning, and artificial intelligence, including number 1, data science, the process of using statistical and computational methods to extract insights from data. Number 2, tools and techniques, overview of the various tools and techniques used in data science, including data collection, cleaning, visualization, and modeling. Number 3, statistics and probability, a basic understanding of key statistical concepts, including hypothesis testing and regression and classification. Number 4, machine learning, introduction to the different types of machine learning algorithms, including linear and logistic regression, decision trees, support vector machines, and neural networks. Number 5, artificial intelligence, definition and history of artificial intelligence and the various types of AI and their applications, including natural language processing and computer vision. Number 6, bias and ethics, overview of the challenges and ethical considerations surrounding AI, including bias, fairness, and accountability. Overall, this course aimed toward provide a comprehensive introduction to data science, machine learning, and artificial intelligence, and to equip you with the knowledge and skills needed to tackle real-world data science problems. We hope that you found the course informative and engaging, and that you are now ready to apply your new knowledge to your own data science projects. Opportunities and challenges in data science, machine learning, and artificial intelligence. There are many opportunities and challenges associated with data science, machine learning, and artificial intelligence. Opportunities. Number 1, job growth. Data science, machine learning, and AI are growing fields with high demand for skilled professionals. Number 2, business insights. Data science enables organizations to gain valuable insights into their operations and make data-driven decisions. Number 3, automation. Machine learning algorithms can automate repetitive tasks, freeing up time for more important work. Number 4, improve decision. AI can help organizations make better decisions by analyzing large amounts of data. Number 5, personalization. AI can be used to personalize products and services to meet the needs and preferences of individual customers. Number 6, predictive maintenance. AI can be used to predict when equipment is likely to fail, enabling organizations to perform maintenance before problems occur. Challenges on data quality. Number 1, quality of data can greatly impact the accuracy of data science models. Cleaning and preparing data can be time consuming and challenging. Number two, bias. Machine learning algorithms can perpetuate existing biases in data, leading to unfair outcomes. Number three, regulation. There are increasing concerns about the ethical and legal implications of AI, and regulations are being developed to ensure its safe and responsible use. Number four, interpreting results. It can be challenging to understand the results of complex data science models and explain them to non-technical stakeholders. Number five, technical expertise. Data science and machine learning require a high level of technical expertise, and staying up to date with new developments can be challenging. Number six, computational resources. Training large machine learning models can be computationally intensive and require significant resources. In conclusion, data science, machine learning, and AI offer many exciting opportunities, but also present significant challenges. It is important for organizations to consider both the potential benefits and the potential risks when implementing these technologies. Suggestions for further learning and resources. After completing this course, there are many avenues for further learning and exploring the field of data science, machine learning, and artificial intelligence. Here are some suggestions and resources that can help. Number one, online courses. Websites like Coursera, Udemy, and edX offer a wide variety of courses on data science, machine learning, and artificial intelligence that are taught by experts in the field. These courses provide an in-depth understanding of the topics and allow for hands-on practice with real-world problems. Number two, books. There are many books available on data science, machine learning, and artificial intelligence that are written for both beginners and advanced learners. Some popular books include An Introduction to Statistical Learning by Gareth James, Hands-on Machine Learning with Scikit-learn and TensorFlow by Aaron Garam, and Deep Learning by Ian Goodfellow. Number three, research papers. Staying up to date with the latest research in the field is an important aspect of further learning. Some popular websites to access research papers include ARXIV, IEEE Explorer, and Google Scholar. Number four, participating in Kaggle competition. Kaggle is an online platform for data science and machine learning competitions where participants can work on real-world problems and gain hands-on experience. Number five, attending conferences and workshops. Attending conferences and workshops can provide opportunity to network with other professionals in the field and stay up to date with the latest developments. Some popular conferences include the Conference on Neural Information Processing Systems, the Association for Computational Linguistics, and the Conference on Computer Vision and Pattern Recognition. These are just a few of the many resources available for further learning in the field of data science, machine learning, and artificial intelligence. The important thing is to keep learning and exploring new topics and techniques to continually improve your skills and knowledge.